Suppose now that we want to calculate the force carried by brace EI on the other side of the concrete pour. We have to begin with a free body diagram as we did in the previous example, but this is complicated by the fact that the right side of the pour is inclined at an angle. Three possible free body diagrams are shown in this figure. Which, if any, are accurate? Take a minute to think about this and resume playing when you are ready to hear a discussion. One of these free body diagrams is correct as sketched. The one on the left has an error. The pressure is shown increasing linearly with depth, but the direction of the pressure is wrong. It isn't normal to form DEG. The free body diagram in figure B is correct. The free body diagram in figure C has an omission. What is there is fine, but we're missing the pressure distribution on the bottom of the form. We aren't given a specific angle of inclination of form DEG, so I'm going to assume a value. I'm going to take it equal to 80 degrees from horizontal, and I'll compare the solutions using the free body diagrams in B and the corrected one in C. So now let's take a look at those solutions. So for illustration purposes, I'm going to take this angle to be 80 degrees, and that's going to require us to find a couple of distances. The first is the length of DEG itself. So the vertical drop from the top of the form to ground is given as 3 meters, and that means that the sine of 80 degrees could be written as the depth at A, the 3 meters, over the length of DEG. If we turn that around and calculate that length, the length of DEG is equal to 3.046 meters. It's also going to be the case that our force carried in member EI exists at a vertical elevation of 1.7 meters from ground, and so we're also going to need this distance x. We could say that tangent of 80 degrees is equal to that height at E, 1.7 meters over x, and if we turn that around, x is equal to 0.3 meters. Now the forces we have acting here include FEI, it includes dx and dy components at these locations, and then we're going to have a resultant force from the pressure distribution roughly here. I'll call it R, and this distance from the base here, this is going to be 1/3 the length of DEG between here and here. The value of that resultant force is just the area under the triangle, 1/2 the line load value at A times the length of DEG. So we calculated the line load at A previously. That was 8.476 times 10 to the 4th newtons per meter. Now we have a slightly longer length of DEG. That's 3.046 meters. And that gives us a resultant force that's equal to 129.1 kilonewtons. So just make a note that that's a different force than the force P we calculated in the previous example. In that case, the value of P was 127.1 kilonewtons, and it's because of the different length over which that line load was acting. Now we're again going to find the force in EI by taking moments about D. Note that in this case we will have contributions both from the horizontal and vertical components of EI. This angle here is 40 degrees. And the horizontal component will be exerting a counterclockwise or positive moment through a moment arm of 1.7 meters. The vertical component will be exerting a clockwise or negative moment through that distance x that we just calculated above. So if I take sum of the moments about D and set that equal to 0, I have FEI cosine 40 times its moment arm of 1.7 meters minus FEI sine 40 times its moment arm x, which is 0.3 meters, minus my resultant force R times 1/3 of the length of DEG, which was 3.046 meters. And that's equal to 0. And if I rearrange this expression for FEI, I can write this as R, which is 129.1 kilonewtons, times the 3.046 meters divided by 3 over this denominator, and that result turns out to be equal to 118.1 kilonewton. So we'll keep that number in mind now as we look at our second solution. Before we look at that second solution, let's just go up here and fix our free body diagram at C and make it respectable. So what we're missing here is a pressure distribution on the bottom that looks like this. The magnitude of this is the same as the magnitude of this. It's the same depth. So we're going to use that as our basis of our free body diagram. Now we should note that the pressure distribution we have on the left side looks exactly like what we had in the previous example. So I've already calculated that resultant P. It's going to be 127.1 kilonewtons. It's going to act a third of the way up from the base. It's going to be 1 meter. What we will have to do is figure out the weight of the concrete that's inside between the vertical cut and the surface of the form DEG, and we'll have to calculate the normal force acting on the bottom of this concrete. So let's go back now. So we'll go ahead now and draw our free body diagram again, now including the concrete between form DEG and the vertical cut. We already know this force P. We calculated that before. That was 127.1 kilonewtons, and it's 1 meter from the bottom. We're going to need this length L, and we can again say that tangent of 80 degrees is equal to the depth at A over the length L. And if we turn that around, L is equal to 0.529 meters. We're going to have our pin supports here, dx and dy. We're going to have our force in EI. Again, that makes an angle of 40 degrees with the horizontal. And now we have a uniform normal force at the bottom, so that's going to be a distance L over 2. I'm going to call that N. That's going to act a distance L over 2 from D, and we're also going to have the weight of the concrete here, and because of that triangular shape, that's going to be 2L over 3 from D. So we'll calculate some values here. For the normal force, we have the pressure at A, the hydrostatic pressure from the concrete, times the span S times L. That's equal to the line load at A times L. And if we plug in 8.476 times 10 to the 4th Newton per meter for the line load at A, times this length L of 0.529 meters, we end up with 4.484 times 10 to the 4th newtons. If we evaluate the weight of the concrete inside, that's a specific gravity times the volume, which is 1/2 times the depth at A, the 3 meters, times the length L times S. We might note that that's 1/2 the pressure at A times LS. So this value is actually going to be just half of N. It's going to be 2.242 times 10 to the 4th newtons. So again, we'll take moments about D and set that equal to 0. Now we have the weight times 2/3 L minus N times L over 2 minus P times 1 meter, and then plus the contributions from the brace EI. all of that equal to 0. Now we can just note that this n is actually equal to 2w, so those first two terms will give us a net minus w times L over 3, and we could rearrange this as p times 1 meter plus w times L over 3 over 1.7 cosine 40 minus 0.3 sine 40 meters. And plugging in 127.1 kilonewtons for P and 22.42 kilonewtons for the weight, and L equals 0.529 meters, this ends up giving us again 118.1 kilonewtons for the force carried by the brace EI. So what these two solutions show you is that you can do the problem, as we've found many times in the past, one of two ways. If we do the problem consistently, we should get the same result either way. The solution of example 4, based on the free body diagram in C, is most useful when the fluid is adjacent to a curved surface. As an example, consider the firefighting aircraft shown in this and the next slide. Here there is a compartment in the belly of the plane having a rounded gate that matches the shape of the aircraft's fuselage. The compartment is filled with fire retardant, and the plane takes off, makes its way to the forest fire, and dumps its load. The mechanism that holds the retardant in place must exert a certain threshold force to keep the gate closed. Here we have a model of the compartment in the belly of the aircraft. We are told the retardant has a specific weight of 69 pounds per cubic foot, and that one of these control mechanisms exists for every 8 feet of fuselage. We are asked for the minimum force the control rods must exert if the tank is completely filled. One of the ambiguities of the problem statement has to do with what is meant by completely filled. One interpretation is that we fill the compartment up to the ceiling, in which case the depth of retardant at B is 4 feet. If we are pumping the fluid into the compartment and can exert some overpressure beyond atmospheric pressure, then we might be able to fill it up a little further, up to the top of the lower U of the air vent. This requires an overpressure of the specific weight, 69 pounds per cubic foot, times the depth, 1 foot, and converted into PSI, that turns out to be about half of a PSI. I will assume this capability exists so that the pressure at B is based on a depth of 5 feet instead of 4 feet. The other thing to note are the little triangular icons between the curved pieces between C and AB. These are intended to indicate that the curved pieces are welded together. This is a rigid connection, so that the gray ABC piece is to be taken as a single rigid body. Let's now take a look at the solution. Given the curved surface of the gate, it is easier to draw an enveloping surface that captures a portion of the fluid above the gate. So I'm going to make my closed enveloping boundary look like this. I'm going to come over here. I'm going to cut through the pin connection at C and the pin connection at B, and we'll go straight up this way. So my free body diagram based on that enveloping surface now will look like this. I have a pin at B, so I'm going to have BX and BY at this location. I have atmosphere on the outside of the gate, so I don't have any pressure out there. I'm going to end up with this force P. I'm going to have a uniform pressure distribution all along the top boundary of this because it's at uniform depth. And I'm going to have a linearly increasing pressure distribution here. I'm also going to have a weight of the retardant acting at an appropriate center of mass here. I'll divide the pressure distribution on the left boundary here into a uniform piece and a triangular piece. I'll call the force F1 associated with these uniform pieces. The value of F1 will be the same on both sides here, and then in addition to that I'm going to have a force F2 that acts at the centroid of that little triangular piece. So we have a number of different things to calculate before we can figure out what this threshold force P needs to be. So the pressure at B is equal to rho G times the depth at B, and this is the specific weight, so I have 69 pounds per cubic foot. And if I assume that I have the overpressure required to fill up this compartment so that the level of retardant reaches the bottom of the U in the air vent, then the depth at B is not 4 feet but 5 feet. And that provides a pressure at B of 345 pounds per square foot. The pressure at A is 69 pounds per cubic foot times the 2 additional feet, so it's 7 feet, and that's 483 pounds per square foot. The line load at B is the pressure at B times the span, S, which is 8 feet, and that value is 2760 pounds per foot. And the line load at A is similarly 3864 pounds per foot. Now the force F1 is the line load times the length along either the top or the side, which is the radius of 24 inches that's shown there in the figure. So this is WB times the radius R, and that's 2760 pounds per foot times 2 feet. It's equal to 5520 pounds. The force F2, based on that triangular distribution, is 1/2 the base, which is the difference between the line load at A and B, times the height, which is also that radius. So that's 1/2 of 3864 minus 2760 pounds per foot times 2 feet. And that number is equal to 1104 pounds. The weight of the retardant is its specific density times the volume, which is 1/4 of a circular cross-section, times the span S, 69 pounds per cubic foot, times 1/4 pi 2 feet squared times 8 feet, and that number is equal to 1734 pounds. So now, having calculated these values, I'm going to sketch again the free body diagram showing the equivalent forces at their specific locations. The pin at C is shown in the figure as 8 inches from B, so that's 2/3 of a foot. The force F1 is halfway along the boundary of the circle, so it's just half a radius, which in this case turns out to be 1 foot. The force F2 is associated with the triangular distribution, so that's 2r/3 from the apex of the triangle. And then finally we have the length L between B and the weight. Now we can get that location because we can look up the centroid of a quarter circular area, and that turns out to be 4r/3 pi as measured from a set of axes that go through the origin of the quarter circle. So it turns out here that L will be equal to radius r minus 4r/3 pi. And for r equals 2 feet, that turns out to be equal to 1.151 feet. So now if we take some of the moments about B and set this equal to 0, we have the following. We have from the top F1 times a moment arm of r/2. We also have from the left-hand side another F1 times r/2. We have the F2 times 2r/3, and we have the weight of the retardant times the length L. And then finally, the only clockwise contribution we have is minus P times its moment arm, which is 2/3 of a foot. and that sum has to be equal to 0. If we turn that around and solve for P, then we get P is equal to 3 over 2 feet times, we can combine the two F1 R over 2 terms to give just F1 times R. That's 5520 pounds times 2 feet, plus F2 was 1104 pounds times 4 feet over 3, plus we had the weight of the retardant, 1734 pounds times 1.151 feet. And if we calculate all that out, we get a value for P that's equal to 21,760 pounds. Many problems involving gases can be modeled as though the gas has no specific weight. This is possible because at conventional pressures and temperatures, the mass density of gas is 2 to 3 orders of magnitude smaller than the mass densities of liquids and solids. Over modest vertical distances, the increase in pressure due to the mass density of the gas is so small as to be negligible. Let's now take a look at a problem where both gases and liquids are present. Here we have a problem involving a tank with 2 compartments. The left contains a pressurized gas, and on the right we have oil with a specific weight of 0.02 pounds per cubic inch. We want to determine the value of the gas pressure that will cause the gate to begin to open. Here our enveloping surface will involve the gate. We have a pin connection at A. We're breaking contact at B, so there won't be any force there. The gas will be assumed to have a uniform pressure, and so we'll have AX and AY at the pin at the top. The gas will act right in the middle of this with its effective force. And then on the right-hand side, we're going to have 2 forces, one from a uniform part and one from a triangular part, due to the increasing depth of the oil. So we'll have an R1 that's right across from FG, and we'll have an R2 down here associated with the triangular distribution, which will be 2/3 of the height of the gate from A. So we'll write the force from the gas as its line load times the length of the gate L, which will be the pressure of the gas times the span S times L. R1 is going to be the line load at A times the gate length L, and that's going to be 0.02 pounds per cubic inch times the depth at A is 5 inches times the span at A is 20 inches times the length of the gate is 15 inches, and that value is equal to 30 pounds. R2 is 1/2 times the difference in line loads between B and A times L. That's 1/2 times 0.02 pounds per inch cubed times the difference in depth, which is also 15 inches, times S of 20 inches times the gate length again of 15 inches. And that value turns out to be equal to 45 pounds. So now if we take moments about A and set those equal to 0, we have FG times the length of the gate over 2 minus R1 times the length of the gate over 2 minus R2 times 2/3 of the length of the gate is equal to 0. That length falls out, and we just get the force provided by the gas has got to be equal to R1 plus 4/3 R2, and that ends up being 30 pounds plus 60 pounds, or 90 pounds. So the gas pressure is equal to the force provided by the gas divided by the span and the length of the gate, 90 pounds over the product of 20 inches and 15 inches, and that ends up giving us 0.3 pounds per square inch. Now remember that that's a gauge pressure, so that's the pressure above the atmospheric pressure that would have to be provided by the gas in order to start opening that gate.